Okay, let's continue our discussion about the way we can model switch mode power converters in order to, say, transform the time variant and nonlinear behavior they have due to the presence of switches into linear time invariant system that are much more, let's say, easy to analyze, because you can, say, apply all the well-known techniques for linear circuits, like, I don't know, superposition effect holds, and Laplace transformation can be applied to the right transfer function, etc., etc. Okay, so many benefits in managing something which is linear time invariant with respect to a, say, structure which is variable in time and which is not linear. Of course, we have to, say, face some approximations. Okay, for example, I cannot have no more information about what happens each single cycle, or which duration is exactly, say, 1 over the switching frequency, because I don't know, by using this kind of, say, modelization, the peak value of the current wafers, just for example, their root mean square value. Okay, just, say, averaging, I lose, say, something which is in the higher frequency range. Okay, the models that I can derive for this, say, analysis have a validity up to 1/2 of the switching frequency. So this is maximum frequency, and then can be modeled in our linear time invariant modelization. We just mentioned 3 techniques by which there are a lot of techniques, but these are the, say, the 3 basic techniques, the oldest techniques that have been developed in order to derive these linear time invariant models for power switching converter. The first is called the state space average techniques. This is a mathematical techniques that has a, say, well-defined procedure that starts by looking at our, say, time variant circuits to isolate time intervals in which the structure is not varying. For example, in CCM, T on and, let's say, Ts minus T on, so T off, and writing down all the differential equations that you can find for that circuit, and say, express in a matrix way, and the order of the matrix is the number of reactive elements you have in the circuits. So if you have, just in our previous example, an inductor and a capacitor, then you have 2 state variables, and so the matrix are in the order of 2 rows and 2 columns. Okay, and then you have to solve these equations. Then you have to make some perturbation, small signal perturbation of the variable in these differential equations, and then you can linearize in the, let's say, very small signal approximation around a DC operating point. Okay, more or less the same procedure you always apply in electronics when you deal with nonlinear elements, so transistors and diodes, for example. Okay, in that situation, you have to simply consider the fact that reactive elements have different behavior for different frequencies, so you have not just to understand what happens at just one frequency, but you have to plot a transfer function. Okay, and the goal was to derive the most important transfer function we have in power converter, the transfer function that relates the duty cycle, so the command, okay, you put on the control signal of your converter, and the effect on variation of the duty cycle on the output voltage, which is the voltage, which is the quantity you like to control. Of course, we are talking about a control technique, which is the voltage mode control techniques. Okay, we are just looking at the output voltage, we say sense this output voltage, and then compare with some reference voltages that set the target we want to obtain as output voltage. Then, say, as a result of this conversion, we have an error signal. The error signal drives the pulse width modulator that generates the duty cycle. Okay, this is the voltage mode, and we are focusing exactly on the voltage mode. Okay, so it's important to understand which is the relationship between the control signal, the duty cycle, and the output voltage. What we can say about the state space average techniques. In analyzing the system, you maybe understand that this technique always works, okay? Provided that you correctly analyze and write down the state variable equation for all your reactive elements for each of the time interval in which a structure is, say, not variable, okay? A solution can always be found out, okay? It is difficult. Okay, this is a good question because sometimes you can find a solution very easy, okay? Some other one can be much more difficult, okay? For the example I just analyzed last time, which is the boost in the continuous conduction mode, okay? More or less, we have to, say, make some algebraic manipulations and some computations, but then at the end we find out solutions, okay? And then solution, say, brings some important, say, knowledge to us, which is the presence of a zero in the right plane, the presence of two complex conjugate poles, and so the specific forms of the transfer function we are searching for. But as I mentioned, say, last time, just if you put some an extra element like the ESR here, which is always present in real practice circuit, then a lot more, say, computation should be done. Okay, you have to insert another equation, y, this is the output equation, that relates the output voltage to the voltage across the C0 and ESR capacitance. Then you have to relate these to the, let's say, state variables, okay? So the computation is, to say, heavy, okay? The result is that you can have another zero in the left-hand plane, so a good zero here, due to the ESR, okay? And so we can approximate the transfer function in this way. But the way we reach this goal can be difficult, okay? And then what happens if you don't have just two, say, reactive elements, but just, I don't know, look at the Chuk converter. Chuk converter has two inductances and two capacitances. Okay, so you have four reactive elements. So in that situation, once you apply the state space averaging technique for deriving the small signal model of our power converter, then you have to face, let's say, we have to tackle matrices that are of four orders, say 4 rows and 4 columns. Okay, so it can be a lot of computation. So you can find always a solution, but pay attention that you have to have, let's say, the process is very, say, as you can say, algorithmic, okay, because you have certain steps that have to follow, and then you follow that steps, a solution is always, say, found. But can be complicated, and then also the physical behavior, the physical meaning of what you find out maybe is not so easy to, let's say, to understand. So it happens that at a certain point, people looking at a circuit like, for example, the say switch mode power converters, find out that a mathematical procedure like that I say show you for the state space average is something very heavy. It's very powerful, but it's heavy. So, and they understand you consider the fact that you have switch mode power converter, the say the time variant behavior is not due to any components in the switch mode converters, but just due to specific elements that are the switches. Are the switches that with their behaviors that, say, is composed by situation which they are on and other situation which they are off, that induces a time variant behavior. So why I have to analyze a whole circuit in which there are switches, but also linear elements and time continuous elements, okay, like for example inductance, capacitance, resistors, and you say analyze the whole circuits, is not say something that makes sense to say just consider the basic elements that say bring with them the time variant behavior. This is the main question. Okay, so the other two methods that we say analyze in what follows just consider this basic fact. Okay, there's no meaning to let's say evaluate the whole circuit, but just the switches. But they are the time variant elements. Okay, so if you look at say structure like this one, which is a very generic description of any switch mode power converter, you can see that you have an input, VG or Vin in our previous say notation. Then you have the load, and then you have that the power converter is composed by a lot of elements that are time invariant, like for example the capacitors, say also resistors and inductance. But then you have what I called the switch network. Remember the switch network that I introduced to you at the beginning when we talk about the buck. As I said, any kind of converters has inside a specific switch made of active and passive switches that say make possible to say be by say consider the behavior to be considered as something which is time variant. So is it possible to extract from our whole network just the switch network composed by the switches, and then considering this switch network as a let's say network that I can analyze by their own. I want to analyze just this network. And then when I analyze this network, I put this network in a time variant and then linear form. I can say re-include my converter, and then I say analyze the whole converter with this model inside it. If you think about this kind of consideration, you have to understand that this consideration is not far away from that you already know. As electronic students, you have, say, met several times the situation in which you have to analyze a circuit in which you have nonlinear elements. For example, a transistor. What you can do when it is asked to derive, I don't know, the amplification of a circuit in which you have a transistor. Okay, let me share the whiteboard. So if you have, I don't know, a circuit like this one, which you have a polar transistor, and then you have a circuit, a biasing circuit like this, and then you have RA, RB, and RC like this, okay? And you are asked to find out, I don't know, the amplification between V0 and V signal, okay, like in this way. What you can do, you linearize all the circuits, including the resistors, then capacitors, or just you consider what happened, say, extracting your, say, nonlinear element here and modelize it by, I don't know, model like this one. At its base, emitter and collector port. Like this. And then when you find out this circuit here, then finally you can say re-include this circuit in your original circuit, you switched off your, say, DC quantities, and then you analyze the circuits. Okay, this is exactly the same situation. I have no reason to, let's say, take the small signal of all the circuits, but just of the nonlinear elements that, say, is the reason why you have this, let's say, nonlinear behavior of the amplifier. So using this kind of, say, reasoning, it makes sense to understand that something, say, faster, if you want, reasoning directly on the circuits can be done in order to model switch mode power converters. Okay, so look at what happens here. Then you have a list of all the topologies that we, say, learn. Some are the basic topologies, the buck, the boost. Some are derived from these two. Okay, some the buck boost or the chook. And you can see here that for all the circuits, you can have a network in which you have just this time variant behavior. This is, as I mentioned before, the switching network. So the switching network, remember that I define here in the back, okay, here as the network in which we have the switch and the diode. Okay, and also I named the, say, the terminal nodes of the network. I called A, that stands for active, because this is connected to the active switch. The MOSFET is an active switch, something that I controlled by specific gate source voltage here. Then there is a node which is called P, which is the node connected to the passive switch. And the passive switch is the diode, something that their turn on or turn off cannot be controlled by external signal. Depends on the voltages and the currents on the circuits in which this diode is inserted. And then you have a common node, which is always the node that connects the active and the passive switch. Okay, so this is a network indicated here, and this network always, say, is included in all the, say, topologies. Okay, you can see here in the boost, you can see here in the buck boost, and you can see it in the choke. So it's not important the polarity of the diode. For example, here the passive node in the buck is connected to the anode. Okay, here is connected to the cathode, but anyway, it's connected to the passive switch. Okay. Here, the active node is connected to, let's say, the source of the switch, and this is connected to the drain. But the active node is always connected to the active switch. Okay, so the general description is that you can have this kind of network. Okay, even this, okay, is the same reason in the choke. You have the passive, the active, and then you have the common, which is the node that connects the two switches. So we can isolate this network, and the network is derived in this way. Okay, just putting two ideal switches because I just talking about, say, ideal behavior. Okay, just to focus on the components. Then we can, say, add some non-idealities, and this can be done after. Okay, so it's like that you have a transistor, and then you can derive the model for your ideal transistor, that you can put, say, something which is non-ideal. It's like the base resistance or whatever you want to include. But anyway, this is the switch network that you can always find out in any kind of topology. Okay, so it's made by a switch here. This is the active switch, and this is commanded by the duty cycle D. And this is the passive switch, okay, which is made turn on and turn off when the active switch is closed or is open. Okay. Let me define for that specific circuit specific voltages and currents. Okay, so let me share. They are indicated here, but let me share the whiteboard to stress these definitions. Okay, so let me change the page. Let me change the color. Okay, here you have switch. This is the active switch, so it is connected to node A. This vertical one is the passive switch, and this is the common node. So let me define this. This is a tripole. Okay, this has 3 nodes, as you can see here. So it's connected in this way. So you have, say, 2 ports. One is on the left side and one is on the right side. Okay, this is the current which is called AI. So IA, sorry. This is the voltage that we can call VAP because it is, say, across the active and the passive node. This is the VCP, and this is the current IC. Okay? So we can define and we can analyze in general this kind of structure. This is called the switching network. The method that I'm going to describe here is called PWM switch averaging method. Okay, and the name stress the fact that I'm going to average just the pulse width modulator switch, so the switch network. Just say comments on this network that can be made on, let's say, the slide. If you see at the common node here, the node C, there is always connected an inductor. Okay, here, and here. Okay, 2 inductors here. They are connected in this way. At the active node here, typically they are connected a capacitor. Here, and the same happens here. You have the capacitor here. You have also this capacitor here. The active is here, and the active is equal here. There's this capacitor here. Okay, so just to have, we can say that this always happens. Okay, so this is our model. What kind of equation we can write down for this tripole? We can say that the current IA of T, which flows in the, say, left side port, is equal to what? Then now we have to divide into 2 different domains. Okay, let me just describe what happens in a continuous conduction mode. So we are operating in the converter in continuous conduction mode, meaning that you have 2 different time intervals in each cycle TS. This one, the first one is T on or T1, which is switch, the active switch is closed and the passive switch is open, and then T2 or T off, in which the opposite happens. So what happens when, for example, we are during, let's say, T on? So when the main switch, when the active switch is on. When the active switch is on, meaning that this is closed, okay, and the passive switch is open, then the current IA is the same of the current IC. What happens during the time interval T off? T off means that you have DS up to, say, TS. Now we have the situation in which D is open, and let's say the passive switch is closed. So in that situation, the current IA is of course null because the main switch is off. Okay. What happens to the voltage VCP? The voltage at the, say, left side port of this tripole. Again, 2 different values because we are reasoning in CCM, so we have 2 different time intervals in which the behavior is not, say, time variant. So for the time interval in which you have T on, in that situation, the switch is closed, and so VAP is the same as VCP. What happens when during T off the switch is open? Of course, VAP is null. Okay, so we have this behavior here. Remember that when I describe the operation of this kind of switch network, I said that the switch that I can command, which is the active switch, so this, say, horizontal switch here, is commanded by a function which is a square function or rectangular function, which can be considered as a logical function that has 0 level and 1 level, that when the switch is closed, Q is 1. When Q is 0, the switch is open. Okay, so we have what is called the unitary switching function. Q as a function of t. For example, let's say something like that. We have Ts, and then we have a time interval like this, in which the Q function is 1, so it means that the active switch is on, and then the passive switch is on. Okay? So we can express the results that I gave you here for the current and the voltage as a function of this switching function. So we can say that, for example, IA of t is simply written as ICT multiplied QT. Okay? Since QT is 1 during T on and is 0 during T off, this expression here is exactly the same of the expression that I gave you before. Okay? So the same for VCP over T. So we can say that, sorry, this is not VCP, this is VAP. Pay attention, VAP is the voltage here, okay, at the input port. VAP is VCP multiplying QT. Okay, so you have these two equations that describe the behavior. Okay. Now, let me put these two equations that describe the tripole, say, this switching network, into this is the instantaneous domain. Okay. All the variables, they are instantaneous variables, into the average domain. So try to describe averaging IA and averaging VCP. Oh, sorry, VAP. Pay attention. I made this error here. So this is exactly, this is VAP. It's VCP, but this is VAP. Sorry about that. So VCP, now I'm looking at this voltage here at the right hand side, which is equal to VAP when the switch is closed. The switch, say the active switch is closed. And this is 0 when the passive switch is closed. Okay, sorry. Sometimes I miss some, say, variable here. Pay attention, VCP, and this is VAP. Okay, so it's VCP, VAP. So I'm looking for the current at, let's say, the left-hand side and the voltage at the right-hand side. Okay, this is the correct way to, say, analyze this thing. And this, say, is evident here. So this is VCP, exactly. So I stress the error they made by the red colors. Okay, so IA is averaged, and so this means that I have to average this quantity. And the same happens here. This is VAP over T as a function of T multiplied by the unitary switching function. Okay. This is the average quantity. Now, I want to exploit a, say, specific result, which is this one. If you have the unitary switching function, like, for example, the one I draw here, and I consider the average value of the unitary switching function, so the average value is, for example, let's say something which is here. Okay, this is QT, the average value over TS. The average value over TS is given by what? It's given by the area here, so which is T on multiplied 1 divided TS. So this is exactly the duty cycle. Okay, now the duty cycle is something that changes with time because we are not in steady state, so we can write down with a small letter. Okay, so the average value of the unitary switching function is exactly the duty cycle. So I want to write down this equation, exploiting these features, so getting, say, putting here the duty cycle. So you have to do something like this. I have to, say, break down the average, and I want to say something like that. VAP as a function of t, average value, Q average t. If this is true, I can say that this is IC capital letter, even this is variable, so it's an average value, multiply the duty cycle, and this is VAP, multiply the duty cycle. Okay? But there is a problem, because this can be, say, good for our modelization purposes, but typical, this expression is not the same. You cannot break down the average of a product of two variables into the product of the average value of the two variables. Okay, this is not, in general, this is not correct. When this is correct? Let's suppose we have this situation. The instantaneous value is something like this. Y as a function of t, then you have the unitary switching function q, and then you have another variable which is x of t. Okay, we are generalizing our discussion. This is exactly the, say, instantaneous expression that we have here. So, okay, we have a variable here, another variable that multiplies a unitary switching function. Okay, so this is general expression when the two variables are called y and x. So we can have that this is the instantaneous value. We can move to the average value, something like, let's say, the x, exactly in this way, which is our goal, only if happens the following condition. Look at the function that multiplies the unitary switching function, that is x. If the average value of x over ds is equal to the average value of x over, say, you can see d over d ts, and it's equal to the average value over 1 minus the ts. So if these three averages computed over the world switching period ts, over just t on, and computed over, say, t off, they are equal among them, then you can have this kind of transformation. So this is true. Okay, this means that you can reply by this equal sign. Okay, if this don't happen, you cannot have this transformation. Okay, of course, this happens when, for example, and this is a consequence, when the variable xt is a constant. When xt is a constant, then the average value over ts is the same of the average value over t on, and it is the same of the average value over t off. So we can say that, okay, you can break the, say, you can break the average over the multiplication into different averages, and then this is correct. And another situation is that when xt is a piecewise linear function. So, for example, I don't know, the current through the inductor, okay, is a behavior that in CCM is something like that, is a piecewise linear function. If you compute, okay, so suppose that this is our variable x over t. If you compute the average of this variable over, say, t on, this is something which is in between. If you compute the average over t off, this is the same value. And if you compute the average over ts, this is the same value. Okay, so this is exactly what happens. But this happens in steady state. Okay, so this is true if you are in steady state. Pay attention, that are the conditions that typically you can find in power electronic circuits. Okay, function like, say, piecewise function, like the inductor current, okay, or say whatever, or variables that are constant, okay, in DC-DC converter. So in steady state, typically this is true. Okay, if you are not in steady state, like the situation that we are examining now in this dynamic situation, we can say that this one, when xt is constant, always is true. Okay, so this can happen. The other situation is that, so in a dynamic situation, you can put the sign equal, okay, because in that expressions, when, let's say, the variables, say, let me redraw, write our expression, generic expression, when y and x, so these two quantities, these two variables, okay, are, let's say, put in this way, frequency separated. What does it mean? That one of the variables has a, say, spectrum which is, say, concentrated at low frequency, and the other variables has a spectrum which is concentrated at higher frequency. So they have, say, totally different behavior in frequency. This is, say, a consequence of the fact that these can be described in terms of, let's say, orthogonal functions in the Hilbert spaces. Okay, so we have orthogonal functions, means exactly that you have two totally, they are not correlated. Okay, they are uncorrelated variables. Okay, and say in electronics, and then you can say that if you look at the frequency, you can say that they are frequency separated. Remember that in our circuits, at the node C, you always have here an inductor. And at the node A here, you have always a capacitor. So what does it mean? It means that the current IC is a smooth current in CCM. It's something that is, let's say, a small undulation. Okay, there is a ripple. In a well-designed converter, the ripple is very small, but has no, say, steep edges. So it's something which is very smooth. And if you can think about of the frequency spectrum, then this frequency spectrum is something which is, say, not include harmonics at higher frequency. Okay, so for example, here you can say that IC is typically something that has a frequency behavior which is concentrated at the low frequency range. what happens to the IA? IA is the current that flows through the switch. And so this is a pulse current. This I in very steep edges, because when the switch is on, okay, it's the same current that through to the output port. But when the switch is off, then the current goes suddenly to zero. So if you look at the current IA in terms of frequency spectrum, then you can see that it has a large number of harmonics at larger frequency range. So IA and IC are separated in frequency. We are not correlated, okay? And so this kind of situation in, say, the dynamic situation leads to the fact that you can have this sign here that these operations can be done. The same happens for the voltages, okay? You have the VAP here is the voltage typically across a capacitor. And so you have smooth voltage drops that say, something which is very, say, quiet, okay? It is not something that jumps, say, up and down. So it's something that in terms of frequency at a harmonic content that can be concentrated in the lower range, while so this happens for VAP. If you look at VCP is something that is here. It's across the passive switch, so it has a very large frequency content, because when the switch is, say, off, then it's the same as VAP. But when the switch is closed, it comes down to zero, say, in a steep way. Even in this case, these two variables, VCP and VAP, are, say, uncorrelated. So this can be done. So we are very lucky in power electronic circuits because we can do these kind of equations. Okay, in, let's say, pulse width modulation power electronics. So at the end, we can say that the average value of the current at, let's say, the left side of our switch network is the same of the average value of the current flowing, say, exiting the right port, multiplying the duty cycle. The average value of VCP, so which is the voltage at the right side port, is the product of the average value of the voltage at the left hand side of the circuit multiplied the duty cycle. Okay, I just included here the time variable because this duty cycle, we are in dynamic situation, is not fixed, change. So this is an average, a moving average. Remember, something that you can have, say, for each, say, time window that lasts for TS. So it changes with the time, of course. So since these change with the time, this relationship here are, say, now are time invariant, okay? Because I averaged it. This average makes the circuit, which originally is time variant, into a time invariant. But these equations are nonlinear, okay? Because you have the product of two variables that depends on time. So we can rewrite here these two equations. Okay, let me put the capital letter to indicate the average. So IA is IC multiplied, and IC depends on T. And then you have VCP, which is VAC. Okay, so time invariant, they comes out from an averaging process, but non-linear. Anyway, just say at this point, we can recognize that these two equations, one for the current and the other one for the voltage, can be represented in a circuit way. Okay, I can use circuits to model these two equations. Okay, which kind of model these equations they remember? Look, we have a current at one side that is the same of the current at the other side multiplied by a factor here. This is the voltage. This happens the same, but for, say, the voltage that are reversed with respect to that of the current. So this looks like similar to a transformer equations. Let me draw here a transformer. Let me put here active. This transformer has just one passive node here. And then you have C. So you have IA over T. This is IC over T. VCP as a function of T. VAP as a function of T. Okay? Which is the turn ratio is the variable duty cycle as a function of T. Is a real transformer this kind of circuit, or is not real transformer? If you look in details this circuit, of course, this circuit is just a mathematical abstraction to model the two sets of the sets of equations. Okay, because it's like the same relationship that you can have in a real transformer. But it is not real for two different reasons. The first one is that it transforms the DC quantities. Okay, any transformers, any real transformer cannot, say, transform DC. It's only transform variable quantities. Okay, so this is something which is not real. It transforms DC. So I put here a mark. And so also sometimes in literature you can find that this is overstressed by indicated with this bar. So this is something which is indicated. This is a mathematical abstraction because this transformer, say, is not something which you can build. Okay. The second fact that say indicate you that this is not a real transformer is that the turn ratio is variable. It's not fixed. It varies with time. Is a duty cycle. Okay, but anyway, why not? We can use in say modeling our circuit. Okay, of course it's not linear because the duty cycle and turn ratio of this transformer is something that can be varied. Alternatively, you can also model this set of equations by using dependent current and voltage sources. Okay, for example, you can say that the node A, in which you have the IA current, this IA current depends on the output current. Okay, depends on the current exiting from this node, and so you can put here a current source, which is a current dependent current source, which is IC T multiplied dt. This is the passive node. And at the same time, you can recognize that VCP over T, these equations state that it depends on the voltage at the left-hand side multiplied with this I. So you can recognize that this is a, say, voltage-dependent voltage source, which has gain VAC VAP, sorry, multiplied with the cycle. Okay, so you can use both of those two models, okay, in our circuit, but this is a large signal model. It's not a small signal model, okay? It's something that can describe operation when the duty cycle, the input and output voltages and currents varies, say, without any small signal constraints. Okay, so this is a large signal model. Of course, for example, these models can be used in simulation with SPICE. Okay, you can put this kind of description. Okay, you can replace your switch network with these models into SPICE. And what is the benefit? You have benefits and you have drawbacks. The benefit is that if you try to simulate a switch mode power converter with SPICE, and in that switch mode power converter, you have switches, you have diodes, then the simulation time can be very long. Okay, if you want to simulate, I don't know, several periods, okay, of the switching period, then you can have very, say, hours of simulation, because when you open and, say, close the switch, then the converter, the simulator, SPICE or LT SPICE, whatever, try to, let's say, reduce the simulation step in order to, let's say, follow the very steep variation of voltage and currents due to the switch operation that you can have inside. Okay, so this means that you can have, say, hour simulation just for, say, a few milliseconds of, let's say, behavior. If you replace your switch network with this large signal model, then you have a time invariant circuit. Okay, so there is no problem about the steep variation of voltage because you have averaged it over TS. So that means that you can gain several order of magnitudes of simulation times. Okay, up to, let's say, down 2, 3 order of, say, or reduce the time of simulations. Of course, you cannot have the instantaneous expressions of the current across, let's say, I don't know, of the current through the inductors, the root mean square value. Okay, you cannot obtain this one. But if you want to simulate the behavior, okay, if the output voltage reaches the correct value, okay, you can do this and you can have, say, very fast simulation. Okay, as I said before, these equations are non-linear, so we have to linearize it. In order to linearize it, always the same procedure can be applied. You have to perturb your variables, applying a small signal perturbation. Then you have, let's say, this can be done for any specific operational DC operating point, and then you have to linearize it. If you talking about simulation, for example, in SPICE, SPICE can, say, manage very well the linearization, or, say, of these models here. Okay, because if you put a large model like this one, for example, which is a classical transformer model you can put in SPICE, and you put, I don't know, AC simulations in order to derive, for example, a transfer function, you need a time invariant, but, say, linear, okay, LTI system. But SPICE linearize this large signal model in the DC operating point. So SPICE does the work for you, okay? Because in AC simulation, you can find the transient function, so the transfer function, for example, just putting this large signal model. It's SPICE that linearize it around the DC point. If you want to do mathematically, then you have to make the, say, classical process that we already known for the state space average, that you have to, for a non-linear system, you have to perturbate your variables, and then you have to linearize around a DC operating point. Okay, so what does it mean that you have to, say, perturbate and linearize? It means that, for example, let me redraw again our expression, because it's simply that going back and forth with the pages. IA is IC multiplying the duty cycle. If you want, this comes out for our, say, because we are lacking power electronics, this can happen, okay, as I said before. And this is VAP as a function of T multiplied dt. So we have several variables, okay, IA, IC, VAP, duty cycle, etc., that can be described in terms of their DC component plus a, say, small signal AC variation. Okay, for example, the duty cycle D as a function of T as a, say, component which is DC component plus a variable component. Okay, so and this happens for all the other variables. Okay, I always suppose that this is a small signal variation. So that means that D is always less than the DC operating point, the duty cycle, the steady state duty cycle. This is exactly the same operation we did in the state space averaging technique. Okay, so let me replace any of these quantities by their, say, perturbation expression. So this is IA, which is equal to IC plus IC duty cycle plus D at VCP plus VCP, which is equal to VAP DC plus VAP AC small signal D multiplying D at. Okay, so I perturbate around the DC point with a small signal variation. Now I can have, say, the multiplication. IA plus IA is IC capital D capital plus D IC hot plus IC D hot plus IC hot D hot. Then you have VCP plus VCP, which is VAP D plus D VAP plus VAP D hot plus VAP hot D hot. Okay, now we can proceed as usual. So we can neglect second order nonlinear terms that are the product of two, say, small signal quantities. Okay, the product of two variables having the odd sign here, the odd sign here. Okay, so we can neglect these. They are, say, second order terms. Okay, they are small signal. When you multiply two small quantities between them, then you can get something which is even smaller. So here you can see that we have something which is, say, totally DC, something which is, say, small signal quantity. So let me just isolate the DC quantity here. DC here, and then here. So, and then let me separate the DC expression. DC terms that are IA is equal to IC multiplying D, and VCP VAP multiplying D. Okay, so this is just comes out from this DC quantity. Again, I can represent in a circuit way. This is another transformer. Okay, this transformer is again a mathematical abstraction because it, say, transformed the DC. We have here the DC quantity. So the DC means the steady state quantity. Okay, this is the DC model of the pulse width modulator switch network. If I remember well, I employed a similar model with using this kind of transformator model when we talk about the boost converter in steady state, in order to understand why in steady state the say the conversion ratio M cannot go up to infinity when the duty cycle is 1. Okay, introducing the effect of parasitics, resistance parasitic that you can have in the circuit. So you can go in that kind of explanation. You can find that I just introduced in that situation a description like this one, because it can be, say, something that can be, say, very powerful to understand something which can be analyzed. Okay, so AC terms, just considering what is not DC, so IA at terms that have a hat on the top of it, so it is IA at, which is equal to IC T plus D IC. And then we have VCP hat PAP plus multiply D plus D VAP. Okay, this is the, I totally separated the two domains, DC and AC. Again, we can model these equations in a circuital way. Okay, we have two terms that are this one and this one, okay? And together with these two, so the green circles here, are, say, something that can be described by our transformer. Our, say, not real transformer, magical transformer. Okay, here this is circuits. The turn ratio now is D. Okay, D is the steady state value of the duty cycle. Here the same. Okay, the turn ratio is D. Then what happens here? That you have, as you can see, this is the summation of two currents. So we can consider this as a node in which you have two currents flowing. Okay, so the Kirchhoff current law. So it means that you can have a current source like this, which is IC duty cycle, and IC is something that exit. Here you have IC here. IC hat, okay, but this is IC DC terms. This is VAP, so this is A, and this is IA at. Okay, so you can see that at this node here, IA is the summation of the current that flow here, that is D AC, plus the current flowing in this current source, current dependent current source here. Okay. In the same way, the voltage equation is just a voltage Kirchhoff law. So we can model as, say, something like this, plus minus. This is VCP, and this is VAP D hat. So it's a voltage dependent voltage source. So this is dependent on VAP DC quantity. This is AC DC quantity. D at is the small signal variation perturbation. Okay. So this is the small signal model of our switch network. Okay, so at the end we derive three different models. One is the, let's say, the DC model, which is this one, just for steady state analysis. The other one is small signal linear time invariant model that we can use for deriving the transfer function. So we can apply superposition effect, we can apply Laplace. And the first model we derived here is somewhere, okay, this one is the large signal model that they can use for simulation in circuital simulators, okay? So this is what happens. Now, as you can see, the analysis is just, say, more circuital with respect to the state space averaging techniques. It's not only circuital, but is just focused on the switch network. Once we derive the switch network model, then we can apply the same model for all the power converters. It's not needed to restart from the beginning, say, looking at the topology and write down the differential equation describing the status of the reactive elements, etc., etc. Because once you have the model for your, say, pulse width modulator switch network, then you can replace, okay, according to the connection of these nodes into the circuits, and then you can solve for small signal analysis. Okay? Exactly the same way you did for, say, the, I don't know, transistor. Okay, you have the model for the transistor, and then you can apply in a circuit, and then you can derive any topology. You have the, say, common emitter, common base, common collector. Okay, they are different topologies, but that the model of the transistor is always the same. There's no need to recompute any time for any topology. Okay, this is the powerful this technique. Just to give you an example, let's consider, say, for example, the DC model. Okay, the DC model is here. Okay, let's see if the DC model is working. Okay, let's this check. As an example, let's try the DC model. Let's try the DC model to derive the conversion ratio for continuous conduction mode of a buck boost. Okay, so we are in steady state. We know that this kind of conversion ratio is, by the way, d over d minus 1. We derive it, okay, by using the volt second balance of the inductor, etc. Let's try to use the model, okay, and that's to verify that you can get the same results. Okay, so let me just to write down to draw the topology of the buck boost. So we have here V in. This is C here. This is the switch. This is the diode L, C naught, and we have the resistor across which there is V naught. Okay, active node is the node connected to the active switch. So this is active node. The passive is connected to the passive switch, and then you have the common node, which is the node which is in common between the two. So we have, this is the switch network. I know which is the model, the DC model for the switch network, because the model of the switch network is something like this. Is 1, D is the turn ratio, and so you have the active node here, the passive node is here, and the common node is here. So the problem is typically now converted into, say, replace my active switch in the original circuit with the DC model, okay, and to derive equations in order to, say, compute the conversion ratio. Let me draw these circuits. It can be a little bit, let's say, this may be the part that you can, say, follow, say, with the, say, higher attention, because you have to connect correctly to different nodes, to, say, to the circuits, in order to, say, avoid mistakes and, say, something that can be not correct. Okay, so the node A here is connected to this say, primary side of this transformer. So we have V in, we have A, and so we have to connect to this primary side. Okay. There are two ways to do this. Or you can consider the original circuits and then you do not move any of these original circuits, and then you connect to ACP the transformer, and then you can do the reverse option. So you can use the transformer, and then you connect to ACP the circuit, the components you can have into the circuits. Okay. In the slide, I choose, for example, the situation in which I just have the same components in the same position. Then I replace the switch network with my transformer. Maybe we can do the opposite. Okay, we can use the transformer with this position, exactly this one, without modifying it. So we have B, we have A, and we have C, and then connect all the other components currently to these terminals. Okay, so for example, from the node A, you have the V in battery. Okay, so you have the plus sign of the V in battery. Okay, the negative sign of this battery goes to this node here. Okay, this node here is the node of the resistor, the minus polarity of the voltage V0. Okay, the positive polarity of the voltage V0 is connected to the passive. So here. Then what happens? That you can see the negative side of the battery here, this node here, this blue one, is also connected to this inductance. Okay, this inductance connects to the C node, the common node. So we have here an inductance which is connected to C. Okay. And then between P and C, sorry, you have the diodes, the model. C naught capacitance is connected between P and so between here and this node is connected between here and the minus node here, so it's connected between here. Okay, and then we have C in, which is connected between A and the negative sign of the battery. Is here. Okay, something like this. We have, remember that this you have here, and then we can have read IC. This is VCP. This is IA, DC, and this is VAP. Now, Remember that we replaced our model into the circuit, into regional circuits, but we are operating in DC. So we are in DC. And in DC means that we have to, say, consider that, say, capacitors are open circuits, inductors are shorts. Okay, so let me modify the circuits by eliminating the capacitances and putting here a short. So this circuit is exactly this one. So this is Vin. So we can say that VAP is equal to Vin minus V naught. Okay, simply a Kirchhoff law here. VCP is the voltage at the secondary of this transformer, so it's simply the turn ratio D that multiplies VAP. So is D Vin minus D V naught. Okay, and VCP, if you look VCP is the voltage across this node, positive, to this one, which is this one. So VCP is exactly minus V naught. So negative V naught. So negative V naught is D Vin minus D V naught. Now, if you look for Vin over V naught, which is our conversion ratio, this is exactly D over D minus 1 for the back. So we are exactly what we're searching for. Okay. So let me interrupt here this lecture. I have some questions to answer. Okay, so let me. Okay, VCIA, VCPT, is it? I don't know what you are referred to. I checked this and I correct it. Okay, I think Porcelli Ivan. I correct this in my my previous analysis. Yes, P and we are switches. Okay, thank you. Okay, sorry about that. I just make some confusion, but say I correct my mistakes. Okay, so Monday we can continue to use the small signal analysis, okay, to derive, for example, a specific transfer function, the Bach CCM, okay, which is something very important. If you have other questions, I can answer. Otherwise, today at in the LED there is the boost open loop. Okay, do not disconnect the load. Okay, because if you disconnect the load in an operating boost, then something bad can happen. Okay, if you want to disconnect the load when the boost is operated, before disconnecting the load, turn off your converter. So it means that you have to reduce the input voltage to 0, and then it can say you can do that safely. Okay, follow what is written in the guideline for that lab. Okay. Okay. Thank you very much for your attention. I wish you a nice weekend. See you on Monday.